Hello, Dr. Atre. My topic is usage of GSM, generative shaping and material forming strategy, and Vat Photopolymerization 3D printing. The title of my paper is Generative Shaping and Material Forming Enables Structure Engineering of Complex Shaped Li4 SiO4 Ceramics based on 3D printing of ceramic polymer precursors. The scope of this paper is to use the GSM strategy to develop a target material phase using the Vat photopolymerization as 3D printing process. The background is that this compound is used for applications like carbon dioxide capturing and tritium breeding in nuclear fusion. This tritium breeding unit is constructed in such a way that it is a lithium-rich ceramic pebble-packed bed configuration. The problems being faced are there are high thermal and contact stresses involved. Limiting packing fraction of the material is also one of the problem. Also, the preparation of this compound is also a challenge. It involves low yield, high costs, and it is time consuming. So 3D printing was proposed as an alternative, and one step ahead is using the GSM strategy to get the target material phase. The materials used for this process are methyl polysiloxane, which is the silica source, lithium carbonate, which is the lithium source. Along with them, a diluent, reactive monomer, surfactant, dispersant, and a photoinitiator are used. The process involved is we make a homogeneous slurry out of these materials, and the performance of the slurry is evaluated, followed by Vat photopolymerization to produce parts that undergo ultrasonic cleaning. Then they are post cured with a UV lamp and dried at 50 degrees Celsius. They are then sintered in a muffle furnace in air for 2 hours at 4 different temperatures to study the effect of sintering temperature on the mechanical properties. Key result 1. In order to completely understand the quality of the slurry, orthogonal experiments were done. In these, all the independent factors that can affect the output parameters are grouped, making a set of experiments. This reduces the number of experiment runs and gives a clear understanding of the trends of different variables at play. The variables for evaluating viscosity are mass ratio of the precursor sources, silicon is to lithium, the solid content, and the dispersant content. On the right side, the table specifies the set of experiments with different combos of these three variables. On the left, we see the shear rate dependent viscosity of the samples. A shear thinning behavior is observed where the viscosity drastically decreases with an increase in shear rate. On the left, we have the result of orthogonal experiments which shows that viscosity decreases with an increase in lithium content. It increases with the increase in solid content and the dispersant content too. Another experiment to calculate sedimentation ratio was also conducted. So the sedimentation ratio is the ratio of volume of the upper clear layer to the overall original volume after settling for a period of time. A lower sedimentation ratio is better because it would mean dispersivity, good dispersivity and stability. It also means that the slurry can be preserved for a good time. So on the right, we can see that the sedimentation ratio decreases with an increase in solid content and dispersant content too. But it increases with an increase in lithium content. It is observed that the solid content is the most predominant factor in evaluating the viscosity of the slurry. This is another result of the study. What's the effect of sintering temperature on the mechanical properties of the final part? So on the left we have the DSC-TG curves of the slurry and the printed sample. This test characterizes the thermal behavior. The samples are made to sustain a thermal cycle which makes us understand the mass loss and the exothermic or endothermic heat flow with respect to the material. We see a sharp peak at about 470 degrees Celsius. So this corresponds to the reaction of lithium and silicon sources to form the target material. Beyond this point, the incremental heat rate is maintained slow and the dwell time is maintained higher to ensure the complete synthesis of the target material. The samples are sintered at different temperatures, after which the SEM micrographs are taken as shown on the right. As seen, the grain size keeps increasing with an increase in temperature, and beyond 850 degrees Celsius we see presence of porosities in the structure. For this application, the sintering temperature is chosen to be 850 degrees because it would result in having smaller grains. Larger grains are not favorable for this application because the tritium ions would take a lot of time to go around these larger grains. And so in summary, among all the other factors, solid content had the most influence in the rheological behavior of the slurry, and using this generative shaping material forming strategy for forming the target material phase is a good alternative to developing raw material, because this study led to parts with better mechanical properties and efficient synthesis of the target material phase. And my personal critique of this research is the idea of orthogonal experiments is very good when you have many parameters at play, and this really gave me a clear picture of how independent factors affect an output parameter.